Back in Calculus 1 and 2, when we used the U substitution or even the trig substitution, we did this change of variables. And the change of variables for multiple integrals is essentially the same as the change in variables for that. Except it gets a little trickier when you're changing variables in 2 dimensions. So what we did back then was we changed from a u to a x, or from x to theta or something like that. So we had something in x where we integrated from a to b to something in u if it was a u substitution, where we have 2 new limits, let's just say c and d, where these things came from the u. If we take a look at u as a function, and then we put a in there, and then so those are going to be your new limits. So we did a couple of u substitutions in this class, and I say, should we switch limits? And a lot of you guys want to come back to the x's. But in terms of the multiple integrals, we don't have a choice to come back to the x's. We need to switch our limits. And in fact, we prefer to switch our limits because we'll see that the limits end up being simpler. So this is one of the 2 things that happen. The other thing that happens is that your dx is going to have to be replaced also. So I think our dx changes into something u prime of x du. So we need to replace our x with something, with the differential is what we called it, but something with a u. I'm sorry, I think this should be x prime of u. I think the u prime is over here. How's it go again? We got. Let me see if I can reconjure this up. So e to the negative x squared dx from 1 to 2. If I do a u substitution, u is equal to negative x squared du is going to equal to negative 2x dx. So we would call this u prime of x. Oh, so I think the u prime of x would go over here. But then somehow we need to bring that to the other side or whatever. And then our integral then becomes integral from, well, integral of e to the u, and then, oh wait, I need an x in there. Let me throw an x in here. And so you get a negative 1/2 or something like that. But the other part of this that I wanted to get at was changing the limits. So you have to put x, this value of x, into this value of x and get a new u value. So I think that's going to be negative 1. And if I put 2 in for x, I'm going to get 4 with a negative. So those are my new limits for this. Yes. All right. So those are the 2 things that happen, and those are essentially the 2 things that happen when we bring this up to multiple dimensions. So this is what happens in Calc 1, and what happens in Calc 3. Let's take a look at this equivalence. if we take a look at our polar coordinate example, let's try to mimic what's happening here for us. Let me start down here. I guess I should have started with the differential because that's what we've been using. For the differential, we have the dA, sometimes known as dx dy or dy dx. We get to replace that with r dr d theta. And so the question is, where did this r come from? And then we justified that already. I told you the book does a nice geometric interpretation of where the r comes from, but I went straight to this idea of a Jacobian. Where we find our differential now is a little bit more complicated because we have two variables going into two variables. And so we said that this is going to be the partial of x with respect to r, partial of x with respect to theta, and the partial of y with respect to r, partial of y with respect to theta. And if you worked out the derivatives of that transformation, you're going to get r. And you'll have sine squareds and cosine squareds that'll cancel, not cancel, but it'll simplify to 1. And you'll eventually get r there. And that's how they got that r for your Jacobian. Okay. Now the other thing for us, the bigger benefit and the bigger reason to transform from Cartesian to polar is because our Cartesian coordinate problem initially started with something that's a piece of a circle. And so when we integrate over a circle, we have this complicated looking function and I'll put just some constant a here. I was going to use r, but r is a variable that we're using. What happens is that there is this complicated looking region that we're dealing with that's circular that makes it hard to integrate over because of the x squared plus y squared relationship. We'd have to, solve for y by itself or something, integrate with respect to x first, and do all kinds of other stuff that was a little bit more difficult. But if we take a look at this, if this was my whole region, do you remember how the r and theta look like in terms of the limits? R goes from what to what? 0 to some constant, and then theta goes from 0 to pi. So we never really looked at what that meant geometrically. But if we were to look at what that means geometrically, if we were to write r and theta as our new axes, how would you graph this region in that r and theta axis? It's a rectangle. It's a nice rectangle. Anytime you get constant limits, you're looking at a rectangle. So this becomes a rectangle. right? So what we have here is a relationship between r and theta and x and y. We know that relationship. It's x is equal to, I already wrote it down below, but I'm going to write it down again. X is equal to r cosine theta. Y is equal to r sine theta. That's a relationship that takes r and theta values back to the xy plane. And so the arrow here is kind of weird. The arrow, we're used to writing arrows or drawing arrows from left to right, but this arrow comes from right to left. That's the transformation arrow. And that's actually what's happening is you're taking a rectangle and you're seeing how it looks back at your original region. So sometimes they call this the pullback transformation. You're transforming from one to the other. So let's introduce some more notation that we're going to be using. Sometimes they call this D, or that's what we have been calling it. Sometimes we call it R, but I think in most cases they call it D. And then what you have here, it's kind of weird. I want to call it your new area or your new region that you're going to integrate over. But really, this is the original region, and this is a transformation that takes that region to your original. I just said original earlier, huh? It's the new region. They call it D star. And so what happens there is that in that transformation, your D star would look a little bit easier to deal with in terms of writing your double integral. This might seem all confusing right now, but it's probably going to get worse. All right. So the key things to watch out for when you are dealing with a transformation like this is, first of all, you want to know what the transformation is, and you want to find a relationship between the original domain to the pre-original domain. I guess sometimes they call it pre-image. And in doing so, you can find your new limits for your integration. And then you need the Jacobian to compensate for that differential change from a dx dy to a, in this case, dr d theta. Okay? So temporarily, let's leave it at that, and then we'll take a look at some examples and see if this kind of makes sense. It's not quite your big picture because this is a specific example, but this is an example that we've been doing. Let's take a look at another example to see if we can relate these pieces again and make sense out of that. So let's just jump to the last problem here, huh? Yeah. Second to the last problem. Let's take a peek at this and see if we can solve this. Oh, now they call it R. Great. So the nice thing is that they give us a transformation, and in most of these problems they'll give you the transformation. If they don't give you a transformation, it's either easy enough to find or you're screwed. So let's hope that they give you the transformation, because a lot of times that's the difficult part in this problem. In this case, we have the transformation given to us. So let's recreate the picture that we had earlier, given the information that they have, and then let's label it with D, D star, and whatever else we need to label it as. So let's start by looking at these points. They say R is a parallelogram with the vertices given by these things. Let's see how the vertices look like here. I can't see them all. So let's draw this picture first. Do I need negative? I need negative x's and y's. Negative 2, comma 8, negative 2, comma 8. Positive 2, comma negative 8, positive 2, comma negative 8. 3, comma negative 7, 3, comma negative 7. And negative 1, comma 9, negative 1, comma 9. It's supposed to be a parallelogram. So this is our region R, formerly known as D. And if you were to take a look at this to try to integrate it, if I were to integrate this, say with respect to y first, I would draw a line parallel to the y-axis. But at some point, I need to change functions. Oh, at another point, I need to change functions. So this, if this was set up as a problem like this, where we were to try to draw this or try to compute this integral directly with this region, I would have to create 3 different integrals, because on this part over here, I go into one function and out another, but then when I switch to go to the next phase over here, I have 2 different functions that I'm going in and out of. Well, one of them is different, but in each case, in either case, I would need to change my integrals. And then after here, I get another different type of function, in and out function. So it's more complicated to do it this way. It looks like it's going to come up to be 3 different integrals if I were to try to integrate this as is. So what we're going to do is we're going to use this transformation and hopefully come up with a new and improved region that we're going to integrate over. And in this region, it looks like we're going to use u and v, because those are the new variables that I have in my transformation. And so there's a pullback relation that has x is equal to whatever. X is equal to 1/5 u plus v. Y is equal to 1/5 v minus 4u. So with this, we will find our differential, but let's do that in a little bit. Let's try to figure out what happens to our points. Okay? So what we want to do is we want to know where these points came from. Now, it's not, I'm just going to state this as a fact, and you guys should just believe me. This x-y relationship with u and v is a linear relationship. This is, if you look at this, you should convince yourself that this is actually a system of linear equations. Linear equations, that means x and y or v's and theta, u's and v's are not being squared or being put in a cosine function. Our polar coordinate is not linear. Our polar coordinate transformation has a theta, has a sine and a cosine in it, so that's not linear. But this is linear. And a transformation, a linear transformation like this takes lines to lines. Okay? So linear transformation, let's write that down. Linear transformation maps lines to lines. what that's going to buy us is that all we need to do is figure out where each of these points go. Where do each of these points go? And I will plot those points. I'll get, from these 4 points, I'm going to get 4 new points in U and V. And then I will just connect the dots and make a rectangle, hopefully a nice rectangle that is going to be, you know, within the U's and V's. Okay? How am I going to do that, though? So what I need to do is let's take one of the points. Let's take the first point, -2, 8. So x is equal to -2 y. Oh, I'm sorry, positive. Yeah, -2, +8. That's this point. And if you put that into the transformation, you're going to get -2 is equal to 1/5 u plus v, and 8 is equal to 1/5 v minus 4u. So now you have 2 equations and 2 unknowns. Solve for the unknowns and then get your u and the v. Okay? And we all know how to do that. So I'm not going to do that. At least not by hand. I'm going to just punch it into Wolfram alpha. But if you have time, you should do it by hand. So Wolfram alpha, I'll just ask it to solve, and I'm going to solve 2 equations. The 2 equations are -2, and I use equals for Wolfram alpha. 1/5 times u plus v. I'll have a comma here. I'll have 8 is equal to 1/5. I should probably put that 1/5 in parentheses. I think it's okay. Times v minus 4u. So those are my 2 equations. My 2 unknowns are u and v, so I'll tell Wolfram alpha to solve for that. And then if I press enter, I should get values for u and v, and then that'll tell me where that point came from. So it looks like u is equal to -10 and v is equal to 0. Let's put that in our notes. I'll include the command in our notes as well. And the result is -10, 0. So that means this point over here goes to -10, 0. And that's where 2, 8 came from. All right? So now let's figure out where the rest came from. So that's -2, 8. So I want to go see where 2, -8 came from. So I'm just going to reuse my Wolfram alpha commands. So my x is +2, my y is -8. And that's +10, 0. Yeah?
When you set up your u and v axis, does it matter which is which?
It doesn't usually matter, but try to go with whatever letter comes alphabetical order. So U first and then V. All right, the other one is 3, negative 7. So back into Wolfram, x is 3, y is negative 7. That turns out to be 10, comma 5. Positive 10, comma 5. That's where 3, negative 7 came from. 3, negative 7. And then the last one is negative 1, comma 9. So negative 1 in for x, positive 9 in for y. And that's negative 10, comma 5. Negative 10, comma 5. So it's not a coincidence that this is a nice rectangular region, and therefore we can have constant limits for our integral. But it is a lot of work to figure out what this transformation is, so that your new region, or your original region, your pre-region, is actually a nice rectangular region. Okay? All right, so that's step 1. The next step is the easy part. It's finding the Jacobian. It's easy because I'm hoping it's easy because we had already talked about it. So the Jacobian is going to be, the notation that we use is the partial with respect to x and y over the partial with respect to u and v. And this is going to be the determinant of a 2 by 2 matrix that has the partials of x with respect to u. Can I just write x sub u and x sub v to say the partial with respect to u and with respect to v, y sub u, y sub v, and the determinant of that. So let's calculate x sub u. The derivative of the first one with respect to u looks like it's just going to be 1/5. The derivative of x with respect to v looks like it's still going to be 1/5. The derivative of y with respect to u, this has a negative 4u, and there's a 1/5 out there, so I'll say negative 4/5. And then the derivative of y with respect to v, that's another 1/5. And the determinant is multiply the diagonals and then times or minus the product of the wings. So 1/5 and 1/5. 1 over 25 minus, and then negative 4/5 times 1/5. So it's negative 4 over 25, so there's a minus in between, so that makes it a plus. That looks like 5 over 25. So this is your Jacobian. It's turned out to be constant. Sure. Yeah, I think it is. What if I say sure with a maybe or with a question mark? It might be true. I have to think about that. Yes, maybe. Ah, okay. I'm not sure. I think it should be, but I'm not 100% positive. All right. So that was easy. Yes, it is.
Sure.
No. Keep running through examples in my head, and they are all true. If you turn parallelograms into rectangles, yeah, it's always linear from parallelograms, and then it's always going to be. Yes. Positive. So if you have a linear transformation, your Jacobian is going to be constant. Because the derivatives of these things will the variables will disappear. Yes. 100% now. Whew. Oh, your brain hurt. Okay, now we can set up the integral. So our integral that used to look like this is now going to be an integral. It's going to, there's one more thing that we need to do, of course. Since we actually are doing the substitution, we need to change all the x's into u's and v's, which will work out okay after you simplify stuff. So let me rewrite the actual problem. This is a double integral over a region R of 20x plus 15y dA, and the dA is our dx dy. And let me do this in a couple of steps. We're going to change our integral to include our new region, that's R star, and then we're going to change our x's into u's and v's and y's into u's and v's, so that's 20, and then the x I think is a 1/5 x plus or u plus v, and then y, so 15 times y, and the y was 1/5 v minus 4u. And then our dA changed into du dv. Now I'll say du dv, but you can really change that into dv du if you want or if you need to. And then don't forget the r dr d theta. The r is like that Jacobian that comes out. So we have this extra Jacobian that comes out here that's 1/5. Okay, and I think this simplifies. Does this simplify easily? And this will be a 4u plus 4v plus this will be a 3v minus 12u. So that simplifies not too bad. So my final integral, because you're going to compute this yourselves, is going to be 4 plus 3. That's 7u. No. 7v minus 8u. And then the 1/5 is a constant that I can either leave here or take out of the integral. And if I decide I'm going to integrate with respect to u first, I go back to my region, R star. My u is this horizontal axis, and that went from -10 to +10. And then my v goes from 0 to 5. Probably should have wrote this down. I keep stressing the inequalities for your integrals. You probably should have wrote this down. U, V. And then again, you'd look back in your picture. U goes from -10 to 10, and V goes from 0 to 5. That'll just help write your limits a little bit easier. So now compare this integral with the difficult looking integral that we had before. This is a lot easier to do. You can do this without the help of any calculators, I hope. And so that's the whole idea for these types of integrals, is that you get a complicated integral with parallelograms that are tilted sideways. You can find a nice transformation, or somebody can find it for you, where it gets translated to something nice and easy like this. Marie had her. For V, I don't know. Oh, yeah, because the V limits just go from 0 to 5 up here. And then that's right? -10 to 10. So remember, we got all these points from Wolfram alpha, and so so we ended up solving 4 problems where we had to find 2 equations and 2 unknowns, and then that's how we got these points. So each of these points is a little bit of work in itself, but once you do that, then you can figure out these points, and hopefully your R star is a nice rectangular region, right? Where did this come from? Somebody pulled it out of their hat. The transformation comes from wanting to set, if you have a tilted parallelogram like this, where all the sides are parallel, you can always find a linear transformation to get that parallelogram by just taking 2 points and then making those 2 points go to 0 somehow. And you can set up like an A plus B or AU plus BV and then somehow solve it for it that way. I'm not explaining it properly because I'm not going to ask you to do it, and you can research it yourself. So parallelograms to parallelograms, linear functions are easier to deal with, but there are more complicated examples. There's some that are related to polar coordinates, where you have an ellipse instead of a circle. So that requires another simple transformation. And then there's more complicated transformations like the last problem in your homework, where it's not a linear function, it's actually a bunch of parabolas. It's like 4 parabolas or something that you'll have to transform back. Okay? Any questions? All right. So I'd like to be done with this. The rest of the questions that they have in the homework, there's a couple of questions where all they ask for is the Jacobian, so all you're really looking for is the determinant. And I think there's one where it goes from 3 dimensions to 3 dimensions, so it'll be a 3-dimensional Jacobian that you'll have to find. And if you want to think of the cylindrical and spherical coordinates, I kind of wrote up quickly spherical coordinate transformation and cylindrical coordinate transformation. That's how it's going to look like. Yeah?
How do you go through the 3 by 3?
It's like the cross product.
Oh, okay.
It's like the number and then the determinant of the 2 by 2 submatrix. Okay. So now the other thing I wanted to talk about was the 4-dimensional cube and sphere. Yeah, 4-dimensional sphere. So just as another exercise to extend your brain, so I think I had a bunch of things. Maybe if I can just look at the notes, maybe I don't have to redo this. Notes. So our notes from spherical coordinates. More spherical coordinates. This stuff. Oh, this should go with the previous page. So we ended up getting I think I'm supposed to multiply this by 2 here. 2. So if we call a circle a 2-dimensional sphere, and then we call a sphere a 3-dimensional sphere, and we call this hypersphere a 4-dimensional sphere, we can see how the equations kind of progress, right? So what's stopping us to go to a 5-dimensional sphere? Aside from your brain hurting and logic. But no, logically, it still kind of makes sense. It just carries over. Just add another variable, right? So that's what I want you to think about. Not too hard. But now we need to start coming up with more variables. So in 5 dimensions, we can come up with an x squared plus y squared plus z squared plus w squared plus, now let's introduce another variable. Let's go uvw backwards. So v squared is equal to r squared. So this is a 5-dimensional sphere. It's a sphere that's being described in 5 dimensions. And then you have v over there. If you solve for v, then you get the top half and the bottom half of this 5-dimensional sphere, and what you would have left is a mirror image or some sort of image of 4-dimensional spheres. So here's your thing that you're going to want to put in an integral, and you're going to want to integrate this with respect to x and y and z and w. So now, instead of a triple integral, you're going to have one more integral. 2, 3, 4. And then we need a symbol for this. I need a Greek letter. Alpha. H. Have you guys seen this symbol? Somebody asked about this, right? Yeah, this is a gamma, capital gamma. So since we're integrating the top and the bottom half, we can double this, and then the integrand will look like a constant r squared. And then here's your first variable, x, your second variable, your third variable, z, your fourth variable is w, so those are the 4 variables. And we don't have a symbol for dv or dA, dv. So let's just say dx, dy, dz, dw, and let's write it like that, but say to ourselves that we can put this in any order we want. So I probably want to go dw, dz, dy, dx. And then what we can say is gamma is the 4-dimensional region. It's a 4-dimensional sphere that describes the shadow, and I'll say shadow in quotes, the shadow so the 4-dimensional sphere given by x squared plus y squared plus z squared plus w squared is equal to capital R squared. And we can go even further. We go 6 dimensions, 7 dimensions, 8 dimensions. Right? And it's just spheres within spheres, spheres, just another higher dimension of the sphere. The thing is that this thing can be calculated somehow. There's, I probably, if you can, try to find a four-dimensional equivalent of spherical coordinates, and that would be great. But this can be calculated directly. Kind of difficult, but it can be done. So if we were to write this integral, maybe before I go to 6 or 7 or whatever, maybe we should think about rewriting this as actual limits for W, Z, Y, and X. So if I put the variables in this order and to say this is how I'm going to want to integrate, I'm going to integrate with respect to W first. So if I take a look at my region, what are my W limits? Well, I'll take my W, solve for it. I'll get the W with a positive and a negative. Right? So the W with the negative will go as my lower limit. And then up here would be my upper limit. And once I do that in 4 dimensions, I go down to 3 dimensions, where it's x squared plus y squared plus z squared is equal to r squared. And so if I solve for z squared there, I'll just get a negative r squared minus x squared minus y squared. So that's a top hemisphere, the 3-dimensional hemisphere, and then, or that's the bottom hemisphere, the negative, and the top one is a positive. And then after we integrate with respect to 3 dimensions, we're down to 2 dimensions, which is just a circle in x and y. So if you solve for y there, it'll just be r squared minus x squared, and the negative and the positive sides. And then negative r to r. Constant limits for the end. Yeah?
Back up to our original integral there, we're doing 2 times the top half of the coordinate sphere.
2 times for this one?
Yeah.
The 2, we're looking at the 5-dimensional sphere. We're taking 2 times the 5-dimensional sphere, and then we're doing a quadruple integral, so that's the other 4 dimensions.
So could our lower limits all be zeros, or should they be?
No, this only refers to this, to the 5-dimension part. So if you want to go from 0 here, if you want to change your W from 0 to this, that's another factor of 2. And then you change your Z from 0 to that, that's another factor of 2. Okay. So each time you want to use symmetry, and in this case we're talking about spheres, so you can definitely use symmetry. Each time you use symmetry there, that's another factor of 2 that you need to multiply on. All right. So I bring this up because this would be like section 1511, which doesn't exist in your book, and that would be multiple, the title of this section is multiple integrals, so you're not just talking about double or triple integrals. Technically, there's other integrals that exist that are higher level. Now, for most practical purposes, we don't go that far, but I thought maybe I'd introduce this to you, and if it looks interesting, you can continue to pursue it. And if you want extra credit for the test, the final exam, well, for each of these volumes or hypervolumes or whatever you want to call it, if you find this volume, hypervolume of a 5-dimensional sphere, that would be 1 point, 6-dimensional, 7-dimensional. I'll give you 1 point each, and let's only go up to 8-dimensional. So find volumes of 5D, 6D, 7D, and 8D. And that would be worth 1 point each. So if you decide to take this challenge, you could just do one and be done with it, or you could do 2 or all of them. It's up to you, however many you want to do. Okay, so we'll use the R, capital R, as the radius of the spheres that we're looking at. Okay. All right. Sounds fun, huh? You don't have to do it if you don't want to. It doesn't matter. All right. Wait, let's bring. So the other thing I wanted to do was to take a look at our graphic syllabus. Remember our graphic syllabus from the very beginning of class? I don't know if you've looked at it since. But our graphic syllabus is kind of like our graphic representation of our pathway to happiness. In this class. So if we take a look at what we've done so far, there's some prerequisites that I talked about, and I said you really have to know how to differentiate and integrate, but then, you know, I don't really care about integrating. So, but you should be able to integrate the basic integrals that you would see in Calc 1. So we studied multivariable functions, and we studied vector functions so far. So we actually studied vector functions back in Chapter 10, and then we saw some applications of vector functions with the velocity, acceleration, and projectile problems. So I think the good standard type of problem that we see in these vector-valued functions are the projectile problems. And then we also saw the TNB frame, the Frenet frame, the unit tangent, unit normals, and unit binormal. So we saw that in the vector-valued function. Just this past test, we studied multivariable functions, and then we took derivatives and integrals of those multiple multivariable functions. So we're looking at f of x, y, or f of x, y, z, and then we saw that the derivatives of those involve partial derivatives. And then multiple integrals, we took double and triple integrals of things and changed variables. And basically, we did a lot of that stuff that was covered, analogously covered in Calc 2 and Calc 1 when we took derivatives. And we also got to meet the gradient. And the gradient just seems to be a vector of partial derivatives, where you just make a nice vector out of this. You have partial derivative information about the function, and then you just put them in a nice vector form. Oh, I'm sorry. When I say vector functions here, I guess the projectile should have been down here. So I might have had the, oh no, I had it right. Okay. So we're done with these things, and I hope you're semi-comfortable with them to go on to the next next part, because the next part will be using all those pieces of information, the multiple integrals that we did, the gradient vectors that we've been looking for. We're going to use those pieces of information as we carry on to the next part. Next part, the main focus is going to be vector fields. So just like we had regular functions f of x back in pre-calculus, and then just like we have multiple multivariable functions like f of x, y, and then here we have vector functions r of t, and we put an arrow on top of the r to say that our output is actually a vector. Now we have a new type of function called a vector field. So we're going to introduce vector fields, and then we're going to study vector fields by taking its derivatives and integrals. Now, when I say derivative and integral of a vector field, that's kind of loosely spoken, because when I say derivative of a vector field, there's going to end up being a couple of types of derivatives. And when I say integrals of vector fields, there's going to be a couple of types of integrals. And when I say a couple, that means two or more. So we're going to need to, and some of these integrals will relate back to our double and triple integrals, and some of these derivatives will relate back to our partials and gradients and stuff like that. So let me just tell you now that a vector field is our new topic. And a lot of times we want to denote our vector field with a capital F. And what this does is it takes, I'll just use 2 as an example. It takes a multivariable function and it outputs a multivariable or multivector. Let me say that again. It takes something from 2 dimensions and it outputs something in 2 dimensions. Or you go from R3 to R3. So what that means is that your vector valued function, your vector field, is like a vector valued function, and it's like a function of multivariable. So it takes an input, x and y, and then your output would be a vector. So it'll be the first component of the vector is a multivariable function, and then your second component of the vector will be another multivariable function. So these are the 2 variables coming from the domain, and these are the 2 variables that go out as your image in your range. Okay? So the interesting thing about this is that how are we going to take derivatives, and then how are we going to take integrals of these things? All right, this is your quick intro. Next time we'll dive into vector fields, and then we're going to start taking derivatives.